Assalamu alaikum. Let us discuss Thevenin circuit. So Thevenin theorem says that any linear two-terminal circuit, so linear means this circuit does not have any capacitor or inductor, and circuit has two terminals, so terminal A and terminal B, can be represented with a simple circuit that has only one voltage source and a resistor in series connection with it. So any linear two-terminal circuit can be represented with a simple circuit like this. This simple version of the circuit is called the Thevenin equivalent circuit. So the Thevenin theorem says that any linear or two-terminal circuit, which is this one, can be represented with a simple circuit with a simple voltage source and a series resistor with it, and this circuit is called the Thevenin equivalent circuit. So this VTH thing is the voltage source. The value of the voltage source is called VTH or Thevenin voltage, and value of the resistance is called RTH, but or Thevenin equivalent resistance. Similarly, we can in the lab, our job is to calculate the or find the Thevenin theorem, verify the Thevenin theorem. So we have a very large circuit. So if we disconnect the load, so we have a two terminal. So we have this terminal A and that terminal B. So these two terminals A and B, so this big circuit can be represented with a very simple circuit called the Thevenin equivalent of this circuit. So the Thevenin equivalent circuit would be a very simple circuit with only one voltage source and a resistor connected in series with it. The voltage source is called ETH or VTH and the resistance is called RTH. So in our left sheet, the VTH is known as ETH, is written as ETH, but in the book, VTH is written as VTH instead of V something. And we see in our lab sheet, this VTH is written as ETH over here, and rest of the part remains the same. So in the lab, our job is to verify the Thevenin's theorem. Now let's go back to the theory for a little bit more. This value of this VTH will be, as per the book, it says that this value of this VTH will be the open circuit voltage after disconnecting the load. So if we disconnect the load and we can connect a voltmeter in this position, it will give us the VOC, and this open circuit voltage VOC will be equals to the VTH. So VOC is equals to the VTH. So in the lab, we have to connect a voltmeter after disconnecting the load. So we disconnect this load first, then we connect a voltmeter over here. So just like this, we will disconnect the load first. So RL would be marked as the load resistor. So we will disconnect the load first. It will give us the second circuit of this experiment. So we see that the open circuit voltage can be measured with a voltmeter as shown in the figure. So this open circuit voltage will be called the VOC or open circuit voltage, which is known as the Thevenin voltage VTH. So the voltmeter reading will give us the VTH. In the lab sheet, we see that after we have to connect a short circuit, and the short circuit current is called ISC. This ISC can be measured with from the source transformation, and from the theory part, we know that the short circuit current, this ISC, is also known as the Norton current, IN. So this IN can be measured with an ammeter by measuring the short circuit current. So the Thevenin theorem and the Norton theorem are the same thing. So Thevenin theorem says that any linear two-terminal circuit can be represented with a voltage source and a series resistor, but the Norton theorem says that any linear two-terminal circuit can be represented with a current source and a parallel resistor. In case of Norton, we call it IN and RN, and in case of Thevenin, we call it VTH and RT. So in case of Thevenin, we call it VTH and RTH, and in case of Norton, we call it IN and RN. So these three quantities, VTH and RTH and IN and RN, these are actually linked with Ohm's law. But before that, let us measure the short circuit current. So as we have said earlier, we can measure the short circuit current by connecting an ammeter. So this ammeter reading will give us the short circuit current or the Norton current. We were discussing that these two are related with each other by using Ohm's law, by Ohm's law. So we see that the relationship between RTH and RN is the same thing. So RN and RTH is the same thing, which is the ratio of VTH and IN. So the open circuit voltage will be the VTH and the short circuit current will be the IN. So open circuit voltage is the voltmeter reading, short circuit current is the ammeter reading. So this ratio will give us the value of RTH. Now we kind of got the Thevenin. Since we know VTH and RTH, we can calculate these values of, we can come up with this circuit, VTH and RTH, by experimentally or by calculation or by simulation. So from the simulation, we see that this is our very first circuit. We have already drawn it. Now let us simulate to see everything is okay or not. So we see that after simulation, everything is good. And the load current here, this is 3.260 milliampere. So the current for the first circuit should be that one, which is 3.260 milliampere flowing in the downward direction. So this VL can be measured from the simulation as well. So this VL can be this across voltage across this one. So which is 3.260 minus 0, which is 3.260 volt. So VL and IL can be seen on the screen right now. This means that if we create a simple version of the circuit, which is this figure 4, it will have the same circuit. It will have the same value of the current. So VL will be that value and IL will be that value, which are 3.260 volt and 3.260 milliampere. So VL and IL would be the same in figure 4 and figure 1. So how do we come up with specific values of ETH and RTH so that these two values comes the same? So the trick is we need to open the two terminals and connect a voltmeter as we have discussed earlier. So it will give us the VTH, and the short circuit current, the ammeter reading, will give us the IN. The ratio of VTH and IN will give us the RTH, and ETH is equals to the open circuit voltage VOC, as we have discussed earlier and shown in this figure. So this figure pretty much summarizes everything. Now we can simulate rest of the circuit. So to simulate it, we first copy the circuit. We will not create the same circuit again and again. So I select the whole thing. Now I didn't press anything. Now I press Control C. Then I didn't press anything. Now I click anywhere. Then I press Control V. Now I didn't press anything. Now wherever I want to place this circuit, I click once. Then at the bottom, I click twice. Now our circuit is done. Now in order to get rid of this mode, I press ESC. Now I am out of this mode. Now let us save and simulate to see if everything is okay or not. We see that nothing is okay, something is wrong. We see that this name of this resistor, from the error, this name of this resistor remains same in all three circuits, because we see how this netlist is not created and it is saying in the error that duplicate part name R5. So that means we have different parts that are named in the same. So we just need to change the names. If this is R5, let's change it to R6, 7 and everything, or something else. Let's make it 5.1, 5.2 and 5.3. So now let us save again and simulate, see if everything is okay. Now everything is good. Now this is the same copy of the same circuit, but in order to make it like the lab sheet, we need to create an open circuit over here and short circuit over there. So let's do that. So let's delete this resistor. So now there is an open circuit, there is a short circuit. Let us try to simulate. Oh, not this one, sorry. Let us try to simulate. Nothing is shown because I cannot see the open circuit voltage, because the voltage I can see over here, it's it will be the sum of this thing, but this voltage is not being shown. And how about the current? The current is not being shown over here. So to solve this problem, we can do it in two different ways. First thing to do is to understand is with the resistors. So let us bring back the resistors first. So R, okay, whatever the values of the resistors, we don't really care. So what we really care about is that we need to create a, let's focus on this circuit. We need to create an open circuit over here. So for open circuit, the resistance is infinite. So we can write too many nines, 99999, many nines, in order to make it infinity. And similarly, if we want to make it a short circuit, okay, so we need to focus on this resistor and let's make it of very large value. So let's make it a very, very small value. So in order to make it of very small, Let's put 0 point many zeros and 1. So this will make PSpice believe that this has a very small resistance is a short circuit, and this has a very high resistance as an open circuit. Right now we can save this circuit and simulate. Nothing is happening. I don't know what's wrong. Node is floating. Let us see what's wrong. So let me reconnect them once again and change the values to something very low. So 0.00001 for the short circuit and very high value for the open circuit. So it's like 999. So not this one, but many nines. Okay. So let us save and try to simulate. We still have error. No, we do not have error. I don't know what went wrong for the last time. So we see that the short circuit current here, the Norton current is 6.034, and the open circuit voltage. So we turn on the voltage. The open circuit voltage is 7.09. So we have these values of IN and RN. So IN is 6.034 and RN is 7.09. So RTH will be the ratio of VTH and IN. So after the calculation, we get the value of RTH is 1175. So the value of our RTH gives 1175 and value of VTH is 7.09. Our Thevenin circuit is complete. So this will be our Thevenin equivalent circuit. Now we have to check if this IL matches with our first IL. That means if we have this IL as 3.260 milliampere. So let us do the simulation once again. And let's change the values. So the value of this voltage source would be equals to the 7.09 volt. So let's change the value to 7.09 and the RTH to 1175. So 1175. And IL was the same. So we see that the load resistor was 1 kilo ohm and we have the same value of the load resistor over here. So let us simulate and see if the load currents are the same or not. So simulation is done. We see that the load current for the first circuit and the fourth circuit is the same, which is 3.260 milliampere. So this proves the Thevenin theorem. Now we can also check it for the voltage as well. So we see that the voltage across this 1 kilo ohm resistor is 3.260, and for the main circuit it is also 3.260. Now in the lab environment, we have to first create the circuit as shown in. So let me bring up the figure. So first we make the circuit, we place the resistors as shown in the circuit diagram. To reduce our cognitive load, we will try to make it visually as similar as possible. So after that, we will connect the wires. So this node should be, let me make the bigger. So this node should be connected to this node with a wire. Let me zoom it a bit for you. So these two nodes are already connected, but let me draw it in anyway. So these nodes are already connected, but let me draw it anyway. Now this node should go to the ground, right? So as per the figure, so the bottom part of the 4.7 ohm should be connected to the ground. So over here. So for this, we need to take the ground from the trainer board. From the trainer board, we will see that some of the nodes are marked as ground. So we will put a wire, we will take a wire and connect the ground from this terminal to this terminal. So this is the ground. So here we connected this one. Now we need to connect a 5-volt source to the 3.3 ohm and the 10-volt source to the 1 kilo ohm resistor. So we take the voltage source. So the positive terminal of the voltage source should be connected to the bottom part, this 1 kilo ohm resistor. So let us draw this wire. So this 1 kilo ohm resistor, now it should be not connected. So let me draw the jumping wire in this fashion. So it indicates that there is no connection. It will be connected to the positive terminal of the power supply of 10 volt. Now, since we are taking power from the two different active elements, so we need to make the common ground. So for this, we need to make the negative terminal of the power supply. So negative terminal of the power supply should be connected to the ground of the DC trainer board. So this node and this node must be connected. So this ground part, so this G and D part is connected over here. So this wire, this blue wire, should be connected to this wire. So this means that the common ground has been established because these are the same nodes. Now we can let me draw it in a different way just to make it more clear. So let me draw this ground first. So here, this is the connection, and previously we had the red connection, which is from here. This one should go over here. So now we have the power supply of the circuit ready. Rest of the part is to connect the 5-volt source with this 3.3. So we take this 5-volt source from here. So we connect another wire and connect it to here. So this 3.3 kilo ohm resistance. And rest of the part is to draw the wire. So let us draw this one to that one. But remember, we need to measure the current. So we will put then ammeter over here. So this ammeter will read the current. So since the current is flowing in this direction, so left side of the ammeter should be the positive terminal and the right side should be the negative terminal in this fashion. So here we take the ammeter. So the positive terminal of the ammeter, let's draw it in the red. So this is the positive terminal of the ammeter. So this is the positive of the ammeter. This one should be connected to this node, and the current will flow through this ammeter and will come out from the negative terminal of the ammeter. So this is the negative terminal of the ammeter. So this negative terminal should connect to the load resistor RL. So this one is our load resistor RL. So this load resistor and the bottom part of the load resistor should be connected to the ground as shown in the figure. So we will connect it to the ground. So the ground where is we are drawing it with the blue. So we take this terminal and connect it with this terminal, so making it a common ground. Now our the circuit diagram for the circuit for the first figure is ready as per the diagram. So let us have a look and try to understand if everything is working fine or not. So let us check the circuit diagram, and if it is everything is okay, we can power on and we will see the load current and the ammeter reading should give us as shown on the figure or as much as close to our figure, which is 3.260 milliampere. So the ammeter reading would be 3.260 milliampere for this one. Now if we want to measure the voltage, we can take a voltmeter or we can take the multimeter and make it in the voltage mode. Multimeter, and use it as a volt mode. So we measured the voltage across this RL, which we will have 3.260 or whatever we have. So this is our circuit diagram for the first figure. Now for the second figure, if we follow the workflow, it will take a very less amount of. So if we remember this figure, after disconnecting the load, the voltmeter reading will give us VTH, and the ammeter reading will give us RTH. So now, since the ammeter is already connected, it makes sense to to disconnect the load and measure the IN first. That means we are going to measure this I short circuit current first. Instead of figure 2, let's go to the figure 3 first. It will be. So we see that from the figure 1, if we can simply disconnect this load RL and connect them with a wire, then we will have the ISC. So instead of IL, when we disconnect the load, so this current would be the short circuit current ISC, which is basically our figure 3. So this short circuit current can be measured with this ammeter. So now our job is to disconnect the wire. So we will simply delete this RL and connect them with a short circuit. Or if we do not want to do it, we can simply disconnect this wire and connect it to the ground and get rid of the connections with that RL. So this way RL will be isolated and will not have any effect on the circuit. So right now the ammeter reading will give us the short circuit current. It will not be as shown the figure right now. So the value of the short circuit current will be 6.034 as we have seen earlier. So the value of the ammeter reading will give us the value of the short circuit current. So the short circuit current will be 6.034 milliampere. Now it makes sense to replace the ammeter with a voltmeter because our job is to calculate the open circuit voltage as well. So we will replace the voltmeter with an ammeter. So we will replace the voltmeter with an ammeter. So what we are trying to show is here we had earlier, we had an ammeter, the short circuit current. Now we will replace the ammeter with a voltmeter. So we delete the voltmeter. We delete the ammeter and connect a voltmeter in the same fashion as we had earlier. So the positive terminal should connect to the plus side. So this should be the positive terminal, and the negative terminal of the voltmeter should be connected to the minus side. So here. So this voltmeter will give us the VOC or open circuit voltage, which is the VTH, or in our lab sheet, which is known as ETH. This will be 7.09 volt as shown in our simulation. So right now our job is to calculate our job is to see if the Thevenin circuit is okay or not. For this, we need to get introduced with a new device, which is called the decayed resistance box or resistance decayed box, which is basically a tool to create any value of any resistance. So any value of resistance can be calculated or can be created with this one. So let us discuss once again. I have recorded this video earlier, but unfortunately it was not, there was no audio. So I'm recording it again. The previous residue was over here. So anyway, so this resistance can be calculated. This resistance can be used make any value of voltage. So if you remember our RTH we are supposed to make for this one is RTH was 1175 ohm. So 1175 ohm, or we can write it as 1.175 kilo ohm. So how can we make this kind of circuit? So we need actually a resistor that is of 1175 ohm, and we can call this resistor as RTH. But it's not easy to find this very specific value of this resistor. So for this we use this box, this decayed resistance box. So our first thing to do is to take a wire and wind it here and connect it like this, and we take another wire and wind it here and connected like this. So this whole box will be acting as RTH, and RTH of any value. So now let us try to find out how can we make this RTH of exactly 1175 ohm. So here first thing to notice is that we have lots of switches, and all of the switches are called out and in. So out means off, in means on. So first we have to make sure that all the switches are turned off. So when all the switches are turned off, we have a 0 ohm resistance, but
এখন
now we have
সময়
to make it
সন্ধ্যা 7টা
1075. So we
30
can turn
মিনিট।
on specific switches, and the sum of all those values will give us those specific value of that resistance. So let me explain what I'm talking about. For example, we have this 1 kilo over here. So we can say that this is 1 kilo ohm. So turning this switch on will make this 1000 ohm. Then we can take another resistance, which is this one 100. So this is 1100, 1100. Now we have to still count for 75. So 7 and 5 is there. So we go to this part of the box and turn on these two switches. So turning on these two switches make it 30 plus 40 is 70. So this gives us 70 ohm. Now 5 ohm can be realized by turning on these two switches. So 2 plus 3 is 5. So overall this gives us 70 and this gives us 5 and this gives us 100, this gives us 1000. So some of these all turned on switches gives us 1175. So right now I can consider this box as a resistor of 1175 ohm. I can create any value. For example, I need 3543. I can simply turn on this 3000 button. Then 500, but for the 500 button, I can turn on 200 and 300 or 400 and 100. So either way, I can make 500 and whatever the rest of the part, we get the idea. So we can create any value of the resistor with this decayed resistance box. So now we take this decayed resistance box and let's try to build our circuit once again. So this RTH is now this one and RTH is 1175. So we need to create a circuit like this as shown in the circuit diagram. So we have a very few elements. First of all, we need to make sure that the voltage source have the exactly 7.09 volt. Sorry, so voltage source is VTH is 7.09. So we have to make sure that voltage source from the power supply, that means this voltage source will act as VTH now. So VTH is 7.09 volt. So now the positive terminals of the VTH should be connected to the either terminal of the R, because resistance does not have any polarity. So we can connect with either of the terminals. Now the other terminal of the RTH should come to the load resistor. So the load resistor is this. So let me bring it a little bit to the middle. So the load resistor is connected to the RTH. So in this path, through this path. Okay. So this load resistor RL, the value of RL is 1 kilo ohm. Now we need to measure the current that is flowing in this direction. So this is IL. We are supposed to get it the same as the previous one. So we connect it to the positive side of the multimeter or the ammeter. This one is not the same as we have in the lab. So perhaps we need to make sure that which range we are connecting. Anyway, so the negative terminal of the ammeter should be connected to the power supply's negative terminal as fulfilling the circuit. So right now we will have the ammeter reading and the ammeter reading will give us IL. So we are expected to see the same IL we had earlier. So IL should be 3.026 milliampere. So this proves that this simple Thevenin circuit is giving the same load current as the original circuit of this of our lab sheet. So in the lab sheet, so we have proved that in the simulation and in the lab, we have proved that this IL, that means a big circuit with a load resistor, can be replaced or can be simplified with a very simple circuit with a simple voltage source and a series resistor. So this kind of simple version of the circuit is called the Thevenin equivalent circuit. This voltage source is called the Thevenin voltage, which is the open circuit voltage after disconnecting the load, and the RTH is called the Thevenin resistance, which is the ratio of the voltage, open circuit voltage, and the short circuit current or Norton current. So ratio of the Thevenin voltage and Norton current gives us RTH, which is also known as Norton equivalent resistance RN. So Rn and Rth is the same thing, which gives us the first circuit and the third circuit as the same circuit. So these two, if these two circuits behave exactly equally, so IL for the first circuit and VL for the first circuit should match to the IL and VL of the Thevenin equivalent circuit. So from the simulation, it was quite clear that we see that 3.260 volt and 3.260. Sorry, I maybe perhaps I have written it wrong earlier. 3.260, not 3.026. So 3.260 milliampere. So and for the Thevenin circuit as well, we see the same. So to summarize, first in the lab we will have this setup, and with this setup we need to connect the appropriate wire. So let us practice once again. If you are very good at this, you can skip this part. So we simply draw the wire. Now this part should go to the ground. Now I draw the ground, Now this part should go to the 10-volt source. So I take it to the 10-volt source. Now this part should go to the 5-volt source. Now I connect it with the 5-volt source. This is of 5-volt and this is of ground. Now here it should be an emitter. It should be connected to the positive side of the emitter. So the positive side of the emitter is this, and the negative side of the emitter should be connected to the load. Okay, and the bottom part of the load should be connected to the ground. So we can take this one to the ground, or we can create some other ground point over here and connect all the other things over there. So now this circuit is ready. We have most of the things. Now we will have the load current IL. So this IL will be 3.260 milliampere. After that, we will disconnect this resistor. So if we do not want to disconnect it, we can just replace it. But let us, for better understanding, let us disconnect the load and draw a short circuit. Now this, instead of IL, now this one will give you ISC, or short circuit current. It will be 6.034 milliampere, which is the Norton current, by the way. This is called the Norton current. Now, when we are done with the measuring the current, now we can delete all the emitters. Now it's time for our voltmeter to play. So right now we have an open circuit voltage and the load is disconnected. Now, if we want to measure the voltage, we can simply connect in the open terminals to measure the voltage. So the voltmeter reading will give us the open circuit voltage VOC, which is actually the VTH. In our lab sheet, they call it ETH, which is 7.09 volt. Then next part is calculation. So next part is to calculate RTH. So RTH is 7.09 divided by 6.034 milli, which gives us the unit is ohm, which gives us 1175 ohm. Now we take the decayed resistance box. And try to turn on some of the switches that makes us this 1175 resistor. So we turn on 1100, 30 and 40 is 73, and 2 is 5. And we take the voltage source and make it and adjust it to have the exactly equals to VTH. So this one will be our VTH and this one will be our RTH. So in order to make this circuit, we connect VTH with RTH. So Thevenin circuit is ready. Now we connect the load if it is behaving the same way or different way. So we connect this part to the load. So this is our RL. This is of 1 kilo ohm resistance. Okay, fine. Now the other terminal of the load should be connected to the emitter. So since emitter is passive, so we connect it to the positive terminal, and the negative terminal of the emitter is connecting to the negative side of the battery. So this is the Thevenin equivalent circuit. Now the emitter reading will give us the IL for the last circuit, and we are supposed to see it the same value as the previous one, 3.260 milliampere. So this makes sense. So the Thevenin circuit or Thevenin's theorem is proved. So in the lab sheet, they have told us to do it in a different way. But I'd like to emphasize on another thing before. So let us see the simulation part. Remember, how do we made open circuit and short circuit? There is a smarter way to do it. So previously we made open circuit and short circuit by making the resistance values very big as open circuit and the resistance values are very small to make a short circuit. But the smarter way or the prescribed way in the lab sheet is to connect a voltage source of 0 volt. The voltage source of 0 volt, that means there is no potential difference. This is a short circuit. uh, and current source of 0 ampere will act as an open circuit. So we connect a voltage source of 0 volt and current source of 0 ampere to realize the voltage, the open circuit and short circuit. So we understand that 0 ampere current is flowing. So that means this is an open circuit. No current is flowing. And we have no voltage drop across. So this side and this side, the difference is 0. So there is no voltage drop. Now, if we simulate, we will see the same value, 7.09 volt as the voltage. open circuit voltage, and the short circuit current is 6.034, which is the short circuit current. So the voltage and currents match. The voltage and currents match with the previous one. So this is how the experiment is done. Now we will discuss some part about the theoretical calculations. So we take the main circuit and let's do the theoretical calculation. So we imagine that the mesh current for the first mesh is I1. The mesh current for the second mesh is I2. And the mesh current for the third mesh is IL, as shown in the figure. So this gives us, this is I1, this is I2, and this is IL. So by using method of inspection, we can write the KVL equations directly. So these are the three KVL equations for the first circuit, and solving these sets of equations will give us the value of. Sorry, I think I forgot to put a minus before this I1. So there should be a minus before. So now it is corrected, it should be minus. So the mesh we are writing the equation, that should be the positive and everything else should be the negative. So after calculation, we see that the value of IL is 0.00325999. So it can be written as 326. And since we would like to write it in milliamperes, so decimal point will shift 3 decimal places to the right. So it will be 3.26. Then we can write it milli. So 3.26 milliampere. So which is confirming our simulation. So we have the same value as our IL. So for the second circuit, we can calculate the open circuit voltage. So to calculate the open circuit voltage, we need to find out the voltages on this node, across this node, and across this node. So terminals A and terminal B. So for this, we understand that this part of the voltage is 5 volt. Now the rest of the voltage will be added to this 5 volt to making the overall VOC. So this VOC thing will be the sum of this VOC will be the sum of this 5. So VOC is this 5 plus whatever this voltage is. So we can calculate this voltage. Let's call it Vx. So our VOC will be 5 plus Vx. Now, how can we calculate this Vx? We can calculate this Vx by using mesh analysis. For example, if we take this current as I1 and take this current as I2. So that means the mesh currents for the first mesh and the second mesh is I1 and I2. So this one is I1 and this one is I2. So we can write that Vx, this Vx thing is this Vx is V equals to IR since I2 is flowing in this direction. So we can write Vx is I2 multiplied by 3.3 kilo ohm. So this will give us this Vx. So overall our VOC will be 5. So this voltage source should be added. So this 5 volt. So this 5 volt and will be added to this Vx. So this Vx part is I2 plus 3.3. So we write this Vx part as I2, the sum of I2, and it should be multiplied by 3.3 kilo. So whatever the value of this term will give us the open circuit voltage or Thevenin equivalent voltage. So let us calculate this. To calculate this, we need to find the value of I2. Let us make a fresh version of the circuit and let us write down the KVL equation. So this is the KVL equation for the first. So this is the KVL equation for the second. So solving these two equations gives us I2 equals to 0.633 milliampere. So we can put it in the previous equation and get the value of VOC. So this gives us VOC is 7.0889 volt or 7.09 volt, which conforms with our simulation. In the simulation, we also have 7.090 volt. We shall do the same for the third circuit. So we assume that the mesh currents for the first, second, and the third meshes are I1, I2, and so applying KVL for mesh 1, 2, and 3 respectively, we get these three equations. So solving this set of equations will give us the IN or I short circuit. Sorry, I made a mistake earlier. This should have been plus. So this gives us the value of ISC or IN is 6 point, how much I forgot, 0.006034 ampere. So making it milliampere will give it like this 6 point. We can get rid of this part. So something 6.634 milliampere, which conforms with our result. So we have that ISC as 4.63 6034 milliampere. So now our job is to calculate RTH. So RTH can be calculated by using previous formula as we have shown earlier. So RTH will be the ratio of VTH and RTH. So we calculate the RTH. VTH divided by ISC. Sorry, I told RTH. So VTH is 7.09 and this is 6.034 milli. So the unit will be ohm, so which gives us 1175 ohm. Which brings us to our very last figure, which is this one. So we need to calculate this current IL. So we already know that this voltage is 7.09 volt. So ETH is 7.09 volt, and the current that is sorry, the ohm, that means the resistance, that is 1175 ohm, is the RTH. So we have VTH and RTH values ready, and we know all the values. So we have RTH is this much, VTH is this much. So this is our ETH or VTH, whatever you call it, and this is of 1 kilo ohm. So this is a very simple series circuit. So we can calculate IL from here directly. So by using Ohm's law. So we have this VTH divided by, we have these two resistors are in series. So this one and that one, these two resistors are in series. So we can add them together. So we can write RTH plus RL. So it will give us the overall result. So the overall current will be 7.09 divided by 1175 plus 1K, which is 1000. So the unit will be ampere. So by calculation, we see that the value is this much. So 0.32 blah blah blah. So let us copy and paste this. So the current IL is this much. So if you want to make it milliampere, the point will be over here. So we can get rid of the previous part and let's call it milliampere. So we need to take 3 decimal places. So it will be 259 will be 260. So 260 milliampere. So this is our final answer. So IL is 3.26. And in order to make it happen, that means if the Thevenin theorem is okay, is true, this IL will match to the main circuit's IL, the original circuit's IL will match to the Thevenin circuit IL. So we see that our Thevenin circuit IL is 3.260. Now let's go back to our original circuit where we calculated the current. It was also 3.260 milliampere. So from this theoretical calculation, from simulations and from the lab setup, it will be quite clear that Thevenin theorem is true. So I think I have tried to cover everything from whatever we have it from the lab to the theory part and the everything. So in most of the cases, we will do mesh analysis to find the voltage and currents. We understand that the mesh analysis give us the currents, but we can always use Ohm's law to convert the current into voltage if the value of R is given. So this is how we should perform the experiment. So in the experiment, the job is to make the main circuit. Then we disconnect the load and we connect the ammeter and we connect a voltmeter. Then we construct the Thevenin circuit and measure the current, and we compare these two currents should be the same or at least within the 5% limit. So the theoretical calculation and everything is shown, and the post lab report must be shown. How do we do it? So as we have discussed earlier, the 0 volt voltage source technique and 0 ampere current source technique is already described in the lab sheet. So these lab sheets are very of very high quality. It was prepared long ago by other sir, so thanks to him. So I hope in the theory part it will be even more clear. So in the theory part we haven't yet discussed Norton theorem, and the previous part is Thevenin's theorem. It will be the part of chapter 4. So Thevenin's theorem and Norton's theorem. In the next experiment, we will have maximum power transfer theorem, which is related to Thevenin's theorem, but the next experiment 7 will be a simulation. So thank you very much for watching. It has been quite a long time. Assalamu alaikum.